So we resume our discussion about Debye shielding. Turns out I was a little hurried in what I said the last time, and I would like to revisit it. And there were also a few typos in the in what I had written. So let's do it again. And let me get my pencil back. Right. Okay. So I'm using an updated. I've also updated a few slides in Module 1A. So I don't know why this is not working. Oh yeah. Okay, it did work. So Module 1A is updated. And this is the updated version I'm using right now. Please download the updated version. Okay. Just wanted to say that before. Right. So now, really, the question about Debye shielding is that a plasma comprises positive and negative particles. So on the whole, if you take a really large volume of plasma, it is electrically neutral. There's no doubt about it. But surely you would think that, and as you hold a more and more powerful microscope, so to speak, to the plasma, as you decrease the length scale, at some point you will encounter charge imbalances. Okay, so if you will, if you were moving in one x dimension, you would, if you were really seeing, you would probably see some positive. So this would be Q. Sorry. Q, and say this is 0. Okay, let me erase this. Okay, let me go back to my pencil. So this is 0, and so this would be charge. So at some point you would sort of, as you come smaller, as you come down, you would probably see little positive and negative charge bumps like this. But if you took a large enough scale, okay, if you took a very blunt pencil and sort of smooth things out over, a pencil whose tip was as large as this, for instance, then none of this would be visible to you. It would be the plasma would appear sort of just like that, quasi-neutral. But if the thickness of the pencil was, or if you took a fine enough microscope such that you can discern, you can resolve distances as small as this, or as small as this, right? You would see little charge imbalances. So the question really is, what scales? What are the scales over which electrical neutrality, charge neutrality is valid? Right. Now, if you simply had a bare charge, say a positive charge, the Coulomb potential would simply extend to infinity. Right. The potential R, the phi as a function of R. If you simply had a positive charge sitting here, it would extend to infinity. It would have a 1 over R kind of fall off, right? But in a plasma, in a collection of positive and negative charges, does this really hold? This is the question we're asking, right? And if it holds, over what kinds of length scales would it hold? How small would you have to come down in length scale before you start to see charge imbalances? Okay, so think of taking an electrically neutral plasma, yeah, and slowly, and I emphasize slowly. Slowly is very important. Slowly introducing a small overdensity of protons. You have protons and electrons. Okay, lots of protons, lots of electrons. Now you slowly introduce a small overdensity of protons, slow enough such that the electrostatic approximation is valid. Okay, so this is what I really mean by slowly, and I'd urge you to think about this a little carefully. Okay, now electrons are very mobile, right? Protons are 2000 times more massive, so they're sluggish, they have much more inertia. And when you introduce this, the charge imbalance, the electrons will rush in to neutralize its influence. Why only electrons? We just discussed this. Now, before the overdensity is introduced, however, the plasma is neutral. By definition, that's what we did. We started off with neutral plasma, so there's no electrostatic potential. Okay. Now, due to the charge overdensity, there is now a potential. Okay, and the electron cloud responds with a density that's given by, the density of the cloud is given by Ne e raised to minus E phi over kTe. Okay, and let me see what the next slide is. Yeah, so before that, I will also introduce a different way of, if you are not, I mean, if you're familiar with the Boltzmann distribution, or if you're, I'm sure you're familiar, if you're comfortable with the Boltzmann distribution, then you will immediately accept this. Okay, this is the potential, and this is the thermal energy. K is a Boltzmann constant, and by the way, there's a sign error in Boyd and Sanderson. There should be a negative sign here. So that is one way of looking at it. Okay, here are some particles which are subjected to a potential, and what would the density of these particles look like? That's it. You can simply write it down. If you're not too comfortable with this, there's another way of looking at it, and that's as follows. Let me open my blackboard. Yeah. So now this involves the momentum equation. Think of the electrons as an electron fluid. In other words, there are lots and lots of electrons inside, there are lots and lots of electrons inside this representative macroscopic length. Yeah, so that it's valid to think of it as a fluid. Yeah, and the momentum equation for the electron fluid would be Me dt. This would be, the Ma, yeah, would be and on the right hand side you will have the forces, yeah, minus and this is the new term. As such, this would be fine, and many times if there was a magnetic field, you would write the Lorentz force term, but here we're not dealing with that. Okay. Now you can write this. You can, instead of assuming that we're working in the electrostatic approximation, you can write this as Ne. Now, okay. The other thing is this is a static situation. Okay. So therefore there is no motion of the electrons, and you get that term goes to 0. So 0 is approximately equal to, and so this Ne gets multiplied everywhere, right? Ne E, like that, where phi is the electrostatic potential, where we've written A is equal to, minus grad phi, and there's a minus here and the minus there, they cancel, right? And and since this Ne has been multiplied, we can write now, writing P equals Ne k Te, like that, NKT, yeah. We can oh yeah, so sorry, sorry, where did this any go? I wonder if this is a mistake. Okay, please check. No, I don't. I don't think this is correct. Okay, I don't think this any should be there. I will check this, but it's a minor error. Please check it. Okay. And because there's an any here and an any there, they cancel out. Yeah. Oh, no. This is correct. This is correct. I beg your pardon. This is indeed correct. You are multiplying over. Now the grad PE, however, what you do is you assume an isothermal plasma so that you take the KTE out. Okay. And then the gradient in pressure becomes a gradient in density. This is okay. Okay, so this any will remain. Okay, and now if you solve this for the any, okay, you just take this, for instance, the gradient to be d over dx, like that. Okay, you will find that any is equal to some n cloud, which this is just a normalizing constant, e exponential minus e phi over kte. So this is another way of understanding this guy here. Okay, so this is the equilibrium density of the electron cloud in the presence of an applied potential. And where did this potential come from? It's because of the charge over density. Okay, all right, so let's go ahead now. Right, as before, as we said, the Gauss's law, and using the electrostatic E equals grad phi. You know that so from the Gauss's law is just, of course, divergence of E. Divergence of E is equal to rho over epsilon naught, where rho is the charge density and rho would be E n cloud, like that. Okay. Well, E n cloud minus E n cloud plus E ne, like that. Okay. Why is that? So and over epsilon naught, and so that's what we've written here. Why is this? Why the positive? Well, because prior to the introduction of the overdensity, the plasma is neutral. Okay, and what was the charge density when the plasma is neutral? Well, you just put in phi equals 0 here, and so the charge density before the plasma, before the introduction of this potential, before the overdensity was introduced, when the plasma is totally neutral, is just the electron is just Ne, right? And that's compensated exactly by the positive charges. So in total, the right hand side will be 0, right? If phi was 0, okay. And so even now the n cloud includes the n cloud, of course. Yeah. So the n cloud, of course, includes the effect of the potential. So now the right hand side is not 0, but this simply reflects the fact that when phi was 0, the right hand side is 0. That's all this ensures. Okay, right? Yeah. So this is what I just said. Then what happens is, so this is Poisson's equation, and you write Poisson's equation in this whole thing is grad square phi in spherical. So this is just the right. So this is just the grad square phi in spherical. I've written that, and the right hand side I've just substituted for this n cloud, like that. plus this thing is here. Yeah. And now what I'm going to do is, this approximation is simply expanding the exponential in Taylor series. Yeah. So why is that justified? Because the overdensity is only a perturbation. Okay. So the numerator is much smaller than the denominator, and so this is much smaller than 1. So you're justified in expanding it in a Taylor series. And so the first term of the Taylor series is 1, right? And so for that 1, this guy and this guy cancel out. The second term of the Taylor series involves phi, and when you multiply that with that, you simply get this. So this is the first approximation. 1 over r d over this entire thing, del squared phi, is equal to this. Now we write this as, we club all this together. Okay, we take all of this stuff, all of these, and we write these. This has the dimensions of length, 1 over length squared, this entire quantity. Okay, and that is, as we will see, that's what's called the Debye length. This quantity raised to minus 1/2. This quantity raised to minus 1/2 is what's called the Debye length. So this can equivalently be written as phi over lambda d, Debye length squared. Okay, and so now if you look at the leftmost side of the equation and the rightmost side of the equation, okay, you can verify that the solution is simply this. The solution to phi is, you just plug this in and verify. So there's a 1, and the important thing is look at the solution. What does the solution look like? The solution looks like a 1 over r term and multiplied by an exponential minus r over lambda d term. Okay, so what it is the usual, this is, if this was not there, you would immediately recognize this as the Coulomb potential, right? The Coulomb potential, which due to the charge over density, it falls off as 1 over r. Okay, but on top of that, you've got this guy multiplying it. So this exponential falls off faster than any. If you go far enough, the exponential will always it will always dominate what it's multiplying. Okay. So this would be the bare, quote unquote, the bare charge over density, bare charge over density. Yeah, fine. I would simply say bare charge, but you understand that the charge is produced because of the charge over density. So that's what I mean here. It's killed by this exponential. In other words, beyond, say, about 1 lambda d, beyond, if r is equal to lambda d, you've got exponential minus 1 here. So beyond r equals lambda d, okay, the effect of this is attenuated by e raised to minus 1, or a factor that's larger than e raised to minus 1. So that kills this potential. So beyond 1 Debye length, you can barely discern, you can barely make out the effects of the charged over density. Okay, so it kills it. You go 2 Debye lengths, it's even smaller. That's what you mean by saying that the charge over density is screened. Okay, this is why, or shielded. Screened / shielded. Okay, and so this is what one means by Debye shielding. You go 1 Debye length away, or say a couple of Debye lengths away, definitely 10 Debye lengths away. The effects of any kind of charge is completely shielded. It's totally screened. And next, what we will do is we will look at, so this is one way of looking at Debye shielding. We will look at a slightly more physical, a little more intuitive way of looking at Debye shielding from Sturrock's book.